Hello everyone, this is the second Physics49 virtual SI session. Today is September 30th. I'm Isaiah.
Hello, everyone. Good morning. I'm Hassib.
And today we'll be going over kinematics. So before we go on about the kinematic equations that you all have been applying, let's go over what kinematics is conceptually. So actually, let's do this. Okay. And this is our agenda, by the way. What is kinematics? The definition of coordinate systems, problem, and then we'll go over two practice problems on the worksheet that was given to us in class. So what kinematics is, kinematics. So what it is it's a branch of mechanics that really emphasizes the motion of an object without the influences of forces. So what this basically means is that we only care about where the object is and the speed it's at certain positions. That's pretty much all kinematics is. And this is all done without the influence of forces, which later on in the semester you'll understand. And one of the most important parts about kinematics is the position, because that's really what we're looking for when we talk about kinematics, the position of objects in a certain respect of time. And to do that, a good way to show position is through something called a coordinate system. Hassib, can you go over the basics of a coordinate system and how we could relate it to kinematics?
Yeah, of course. Before I start talking about coordinate systems, I want to ask you something. So when it comes to kinematics, does it matter if it's like a one-dimensional motion or a two-dimensional motion that we're dealing with when it comes to the influence of forces, or it doesn't matter what dimension is the motion is, we don't care about the forces at all?
So we do not care about the forces at all.
Okay.
And it doesn't matter if it's 1D, 2D, or 3D, kinematics affects all dimensions. But for now, what we're going to go over is one-dimensional kinematics.
Okay, I see. All right, so when it comes to coordinate systems, so far in the classes, we've been dealing with a lot of vector values. The vector values, as we know, this could be a question that we can ask the students who are here. What does a vector value represent? Is it a combination of values or a combination of elements, or is it just a number? If there were students, we can wait a little bit, but there's no students at this point, so I'm going to move on. So since vector values give us direction and a scalar value that give us the magnitude, it's important that we find direction with respect to a coordinate system that we put for a problem before starting with the problem. So the importance of the coordinate system comes because they are considered as a relevant direction for all the other respective directions of motion that is happening in the problem. Coordinate systems can be one-dimensional coordinate system, could be two-dimensional coordinate systems, and it's important to identify the coordinate system by the beginning of the problem to make the problem even easier and get the signs correctly for each vector value in the problem. And we'll probably go over an example that needs defining a coordinate system in the practice problems that we're gonna cover by along this session.
So the whole point of coordinate systems is especially important when you're drawing your picture, which is essentially the first step into solving these kinematic equations or kinematic problems. So to really represent that, me and Hassib are going to go over two kinematic problems. One in the x-axis, so we'll define our coordinate system in the x direction, and the other problem, we'll define it in the y direction. So let's go and start with the first problem. If you look here, this is, again, problem number 6 of the worksheet. So let me write that. So a ball rolls across the floor with an acceleration of 0.11 meters per second squared in the direction opposite to its velocity. The ball has a velocity of 4.00 meters after rolling a distance of 6.00 meters across the floor. What was the initial speed of the ball? So again, like we said, we want to start with a picture. So let me erase that. So if we start with a straight line to dictate our floor, and then have a ball over here. So we have a ball that's rolling across the floor with a certain acceleration and a certain velocity. So this is when coordinate systems come to play, because we need to know which direction it's going, and we need to denote that as positive. So we go here, draw a line like this. So for consistency's sake, we will denote that this is the positive x direction, the right side. And then the negative will be on the left. Realize or see how I'm denoting that this is in the x direction or on the x-axis as opposed to the y. So we have a ball, we have our floor, and then we have our axis. Positive x on the right, and positive x on the right, and negative x on the left. So as Hassib said, we need this to denote the direction of the object and where it's going. So now that we have our picture, we need to start labeling our initial points, which is still part of the coordinate system. So let's have the ball start here. Start here. And we'll call this our initial point, or we could say that this is x, not is equal to 0 meters. Right? So this is just showing where my point is starting. Now, Hassib, can I pick anywhere to be my initial point, or does it have to be somewhere specific?
When it comes to initial point for this problem, it will be the point where it will be the point where the ball starts the motion. So if the ball is starting the motion from the position you draw it at, yeah, so we will have only one initial point that we can use, which is the one you denoted. If the ball was on the other side of the axis, or you just happen to draw on a different point than here, yeah, so the initial point will be right at that point, at the point where the ball is. We don't have, but in general, we can make the zero of the axis anywhere as long as we account for that difference. But to make the calculations easy, the initial point is where the object is starting the motion at.
Exactly. So wherever the motion starts, that's where we define our initial point. And that's essentially reported in not just kinematic equations or problems, but the coordinate system itself.
Can I ask you something?
Yeah.
So it looks like okay, you wrote it's x naught equals 0 meters, but is that the same point of the coordinate system being 0, or the 0 point for the coordinate system in a different position?
It's the 0 point at a different position. Remember, we could denote anywhere on here to be our 0 point, as long as that 0 point is where the motion starts in our problem.
Okay, so the 0 point that you put in here, it's the 0 point for the coordinate system, and it's the 0 point for the starting motion.
Yes.
Okay, I see.
So we have that. Another thing we should write is that this is when time is equal to 0 seconds. And this is just saying that this is the moment, again, similar with position, this is the moment that the motion starts. So at 0 seconds, it's at 0 meters, which makes sense, so we're okay. So now we have that. And now we also have this velocity, right? We have this velocity that the ball has. So what we are going to do is make an arrow denoting that the ball is going a positive x direction and at a certain speed. So we have that. And now it says it rolls a distance of 6 meters across the floor. Again, being part of a coordinate system, it shows position. So we have to mark that. We could say that you could denote this as final is equal to 6.00 meters. And this final is just the moment that not the motion stops, but our area of interest where it stops. So we're only looking for when the ball goes from 0 meters to 6.00 meters. So with the ball rolling at this speed across the floor, we also have this acceleration. So Hassib, what is the definition of acceleration?
Acceleration, as the professor defined it in very simple terms, is the change of velocity, is the thing that changes the velocity. So the acceleration will have an effect on the velocity depending on the direction of that velocity. So if acceleration and velocity had the same direction, it will contribute to increasing that velocity. And if the acceleration had an opposite direction of the velocity, it will contribute into slowing down the object to a stop. But the final idea for acceleration, it's the thing that causes velocity to change. Every time there's acceleration, we know that our velocity will be changing.
So in this problem particularly, which direction is the acceleration in?
Well, I'm starting to read from the first sentence, and it says a ball rolls across a floor with an acceleration of certain number in a direction opposite to its velocity. All right, so here you define velocity to be in the positive direction, and the problem's telling me that the acceleration is in the opposite direction of the velocity. So it looks like acceleration will be in the negative direction, which is pointing in opposition of the velocity. Yeah, that is correct.
So what does this do to the ball essentially in terms of its motion? If you have a velocity going one direction and acceleration going the other, what is the ball going to do? Speed up or slow down?
Well, if the ball is going into the positive direction and the acceleration is affecting it in the opposite direction, that means it's probably going to slow it down because of the difference in direction. Because the acceleration and the velocity are acting in opposite directions, the acceleration will have the effect of slowing down the ball. Slowing down the ball.
So we're agreeing that the ball is slowing down to 6 meters.
It's slowing down 6 meters, but I want to ask you something. When you wrote the 4 meters per second, do you mean that it was like constant speed from x naught to x final, or is it 4 meters at a specific point?
So the thing about kinematics here in Phys49 is that the acceleration is going to be constant in these problems. So the ball isn't rolling 4.0 or this number constantly. It's just at that particular moment at 6 meters per second, it's going to be moving 4.0 meters per second. So that's a good catch.
Okay, I see what's happening here.
So at 6 meters, it'll be moving at 4.00 meters per second.
Okay, and all right, and the question asks for finding the initial. So we'll be finding the V at the end. Okay, yeah, that's good.
So do you agree with all the information in this picture?
Yeah, it looks very good so far.
Okay, so the second step into solving these kinematic equations is organizing your known information in some form of a chart. So to do this, we're going to have, if you look here, this, and like this. Okay, so we will have initial values here, and then we'll say at 6 meters. And the reason why we don't want to call this final is because when these problems become multi-state, as in there's more than one position to look at, it's going to be hard denoting everything as final. So we want to be specific.
Okay.
So
you mean like maybe if there is another part of the motion, it will start becoming confusing if we called everything final and final and final.
Exactly.
Oh.
So we're going to give it a specific name. The only reason why we call it final on the chart is because, or on the coordinate system is because that's where the motion ends.
Okay.
So we're here. We're gonna say this is time. Or let's do just t. T for time. X for position in the x direction or on the x-axis. Velocity x and acceleration underscore x. So let's look at time first. Do we know the time initially?
Well, the initial time, it's the initial time of the motion, and if the motion's starting at a certain point of time, it will probably be easy to have that point be equal to 0.
Exactly. So 0.
Okay.
So do we know the time at 6 meters?
The problem doesn't give any clue to what would be the time at 6 meters. So I want to say no, we don't know the time at 6 meters.
And that's okay, right? It's okay to have unknowns.
Yeah, that's fine.
T underscore 6, meaning t at 6 meters.
Okay.
So what about our x, our position?
All right. So for the initial position, I think since we defined it on the graph to be 0 meters, and that's where the starting of the motion. So we'll be using that same point for writing down the data, and it will be 0 meters for our initial position.
Yeah, I agree with that. 0 meters. And then our final is pretty self-explanatory, or not our final, but at 6 meters, it's going to be 6 meters.
It's going to be 6 meters.
So after that, we will, I'm trying to move this across. There you go. So we go here. Now we'll start recording our velocities. So do we know our initial velocity?
When initial velocity, well, the problem it's asking us for the initial velocity, so we don't know it. No, we need to calculate for it, so it will be an unknown.
All right, so v underscore initial x. Like that. Okay. Do we know the velocity at 6 meters?
From our understanding of the problem, and we draw that on the graph, so it will be the velocity at 6 meters will be 4 meters per second.
Exactly. And this is all just according to our picture. This is what makes drawing the picture so powerful, is that we could easily organize or get our information from it and then translate it to our chart.
Yes.
So what about acceleration?
All right. So for acceleration, it looks like it will be constant for the entire motion. And we are given the value for that acceleration. It's 0.1. But I know that we're going to have to start considering, or we need to consider the direction of this acceleration too. So based on how we draw the acceleration on the graph, it should have a negative value because it points in the negative direction.
Exactly. And this is all coming just from the picture. 0.1 squared.
While we write down, I just want to mention that for anybody who joins the session, if you guys have any questions, you can just put it in the chat. We will make sure that we go over these questions.
Okay, and we
And,
said it was constant, so it'll be the same for both, correct?
yeah, it should be the same across the entire motion.
So we'll just go like this.
Yeah, yeah.
Okay, so after writing out our chart and our picture, the next step is writing out our kinematic equations. So let's move this up. Sorry about that. Let's move this up and this up. Oh,
It's becoming too many things
yeah.
at the same time. Again, for anybody in the chat right now, for the students or participating, if you don't have the chat window open, you can have that chat window open if you went to meeting from the top left corner, and there's something that called there's a button, an option that says show chat. That way you can have access to anybody can have access to the chat for this session.
So let's start writing out our kinematic equation. Okay, that's the first one. So the second one is so after that, then we have one more, which is x, and this is all times something called delta x. What
So,
is delta x?
oh, delta x. I know I've seen it somewhere. Isn't it? When we say delta, it means the difference. So when we say delta x, it's the difference in position, and that's probably final minus initial. This is how we have been using it.
Yeah, so delta is equal to final minus initial. Okay, so after that is when we could start plugging in all our numbers. So let's start doing that.
All right, so how about we ask a question, and if we numbered those equations 1, 2, 3, I want to ask a question to the people in the participating. Based on the knowns that we have in this problem, what would be the best equation to use of those three? And the answer could be 1, 2, or 3. We'll take maybe 20, 25 seconds to get this question.
So again, which equation seems the easiest to use in this case, depending on our knowns and unknowns?
So I am looking at it so far, and it looks like we're looking for the initial velocity. We know acceleration. We know the delta x, and we have the final. So far the chat says it's number 3. I want to say it's probably the easiest to go for number 3.
Yeah, and the reason why number 3 is the easiest is because it's the only one that doesn't require time to be used. If we look in our chart, we see that we are missing time at 6 meters. So it's not much use to us. So therefore, we'd have to use, or the easiest one to use would be number 3, right here. So if we plug in our numbers, where this is going to be when is equal to v x plus 2 times and then times delta x, which is just 6. Okay, go like this. Okay, so we have one equation and one unknown. Is this solvable?
Yeah, one unknown, we can solve it.
Okay, so if we solve it, oh, sorry. Then so the answer should be 4.15 meters per second.
And this is after doing all the algebra work for this equation, right?
Yeah, so the algebra work, if you would like to know. So first I squared everything that had to be squared, so we get 16 is equal to v underscore naught x squared. Then I multiplied all these numbers, and you should get negative 1.2. So
Okay.
after that, we're going to add 1.2 on both sides, and then we get 17.2 is equal to v underscore naught x squared. And how do we get rid of a square?
Getting rid of a square. We square root.
Exactly. So if we square root both sides, I will try my best to draw this.
I think it should be understandable to just take the square root of both sides.
Yeah. All right, good enough. So
I like that.
So once we do that, we get our final answer, which is 4.15 meters per second.
So let me ask. I think I'm a little bit. I think I have a problem with something. If we got this answer, where should we put it on the graph? It looks like it's the initial speed, so it looks like I'm gonna put it on top of the ball. But what direction will that have?
So it depends. So if the ball was still moving to the right, it's going to stay moving at the right.
Oh, yeah.
So if we, this is fine to just box it like this, but if we want to put it on the graph itself or on the picture, we put it right here. And say that v underscore naught x is equal to 4.15 meters per second.
Okay, okay. So it was 4.15, and the acceleration was in the opposite direction. It slowed down a little bit to 4 meters per second after a distance of 6 meters. Okay, okay, yeah.
And that makes sense.
Good, yeah, it makes sense.
Since the acceleration is the opposite direction, it'll slow down the speed or the velocity of the ball.
Mm-hmm.
So the thing about kinematics is that it doesn't just function in the x direction. We have also objects moving up and down. So with that, we will be doing another practice problem, which is problem number 7 on your worksheet. And this deals with objects moving up and down as opposed to left and right, or in the y-axis as opposed to the x-axis. So Hassib will be going over how to do that.
All right, sounds good. Can you drop your screen so I can connect my screen and we can start with the problem?
Yeah, so stop share.
Yeah.
Okay. So there you go.
Okay, so what we have here, it's problem number 7. So as we do in a lot of problems in the class, I always have my sheet of equations ready through PCAT. And this is the problem. So what I will do is, the first thing usually to approach a problem is just read the problem sentence by sentence, maybe identify some of the important information in the problem, and we can transfer the problem to a graph. So it says a ball is projected upward. So upward is like a keyword that we can use at a time t equals 0. So it looks like the initial time of the motion is at t equals 0. From a point on a roof 60 meters above the ground. That's an important piece of information that we need. Then the ball rises, then falls and strikes the ground. So it looks like in this sentence they're describing the motion, and they're saying that the ball will go up, rises, and falls and strikes the ground. So we'll go up and go down. The initial velocity of the ball is 71.6 meters per second. So that's an important piece of information, its initial velocity. And if air resistance is negligible, what is the time when the ball strikes the ground? So we don't care about air resistance. We never mentioned it in class. We don't know how to calculate it, so it's negligible here. And we need to find the time when the ball strikes the ground. So we're looking for time in the end of the problem. And so after reading the problem maybe once, you can usually I personally go over it twice and 3 times to make sure that I'm not missing any important information. From what I get so far from the problem is that we're looking for the total time of the motion. So the problem went up and down, and we're looking for the total time spent. All right, so we have an idea of what the motion should be conceptually, so we have to put it down on a graph. So we know it's up and down. Isaiah, you mentioned it's a motion in the y direction. So the first thing that we need to do is define which is positive and which is negative. So I'm going to go here, and I'm going to draw vertical axis that shows, and I'm going to label it where my positive and negative is. So this is my positive direction, and this is my negative direction. All right, then I'm going to have 0, the 0 point to be right here. And since I defined my coordinates, where my positive and negative is, and I define my zero, I will need to see where the motion starts. So on this sentence right here, or not this one, this sentence right here, it tells me that the ball is projected upward from a point of a roof 60 meters above the ground. So that tells me that my position, my starting position, will be 60 meters above the ground. So I'm going to consider, of course, 0 is the ground. This is 60 meters. I'm going to draw something like a roof that tells me, oh, the ball will start from here. And continuing on with the problem, it says that the ball rises and falls and strikes the ground. So it looks like that the ball will go up. I don't know to what point because I don't have that information yet. And it will go all the way down to strike the ground.
So I have a question.
Mm-hmm.
If in this case, does the ball go straight up and straight down, or does it curve like a parabola?
For this problem, it will go straight up and straight down. This is a very important point because the professor could pay attention to the graph drawn by the student. So if it looked like a two-dimensional motion and it's not, that might be a little bit of an issue. So if we want to make it a little bit more accurate in this graph, maybe the edge of the roof will be right here, and the ball went up, and the same line of direction that went down. And
Okay.
this is the point where it reaches, where it goes up and it turns and goes down. So a question that I want to ask for people participating is, at this point, before putting any of the velocities given, what would be the velocity at this point right here? I'm going to take maybe 25 seconds to see what that velocity should be. This point right here, the point where the ball turns.
So in the chat, so far we have the velocity to be 0. And do you think that is correct? Let's see. For the velocity at the apex of the motion to be 0.
Yeah, that is correct. And it makes sense for the velocity to be 0 because if the ball is going up, it has to stop at some point and start the motion back downwards. So that point that it stops on, which is this one right here, it will have a velocity of 0. That is correct. All right, so we'll move on. We'll put down some of the information we still didn't put on the graph. So initial velocity, which is the velocity at this point right here. In the problem, it says that it will be 71.6 meters per second. So we'll put that down, 71.6 meters per second. And the direction for this velocity will be upward because it says that the ball rises, then falls. So we can say that this is V naught, and it will be upward, and the value for V naught will be 71.6 meters per second. Then, if we can look and see if we're missing any other information from the problem. And it looks like this is all the information we have so far. So this is all the information that we can put on the graph. Again, we only know initial velocity. We know the velocity at this point. We can call it v top equals 0 meters per second. And we know the height of the roof. So we'll take this information and as what we did to the previous problem, we're going to write our knowns and unknowns. But before I do that, while I'm doing the table, I want to ask a question. Does this motion look like a motion of two parts, or is it a motion that has one part that is consistent? We'll take 25 seconds to get that question answered.
So the question was, how many parts to this question are there? Or in the motion, how many parts?
Yeah, so does it look like a two-part motion where we have to do two steps to calculate what we need? Or is it one part where it's just one step and we get the answer that we want?
So the chat is saying two-part. Why can we say that this is a two-part, Hassib?
Well, when it comes to these types of motions, we notice that the ball is following two different directions throughout the entire motion, going upwards right here and going downwards after a while. So for us to calculate the time, or maybe I'll go back a little bit back and I'll start saying, it's like, let's ask about the acceleration in each parts of these motions. It will be two parts, but the reason it will be two parts is because of acceleration. So my question right now is, what's the value of acceleration here? Or it will be, what would be the direction of acceleration in this problem, and what is the value of the acceleration? And that would be information that we're going to put right here. So it is correct. It is two parts. Right now, I want to know what is the acceleration in both parts, up and down. And from there, I will start saying why it's two parts. So let's see the acceleration here. And from the initial point till the point it hits the top, what would be the acceleration? Given the fact that we have positive upward and negative downwards. What do you think, Isaiah? What would be the acceleration in the first part of this motion?
So in the chat, we have that someone is saying that the ball going up, it should be negative 9.8. And why do we say negative in this case?
Okay. Do you want to give a little bit of time, or should I go over it?
I think you should just go over it.
Okay, so it is negative for a reason, yes, and that's the correct answer. So since we defined negative to be downward, that's our coordinate system. There's no problem with that. But now we have to think about what's the direction of acceleration. So acceleration always acts on the objects downwards. It pulls them down, which means the acceleration throughout the entire motion will act downwards. So we know always acceleration is equal to 9.8, and that's the magnitude of it always. Of course, it's meters per second squared. But once we're going to start talking about the acceleration that has direction related to this problem, it will be negative 9.8 meters per second squared, because the acceleration, the direction of the acceleration is negative. It points in the negative direction based on how we defined our coordinates. So yeah, that's correct. The acceleration would be negative 9.8, and that will be throughout the entire motion. So this I'm going to leave this information on the graph. I'm just going to take away these because we're going to put it in our table. So we can go back to the table, and we say the acceleration here is 9.8 meters per second squared, and it's across the motion, meters per second squared. But now we can think is like, okay, it's constant across the motion, but why we're considering it a two-part motion? Well, for this specific question, they're asking us about the time. And it's the time spent to go up and to go down. Depending on our knowns and unknowns, we're going to run into a situation where we can't, it will give us the incorrect answer. Or if we started from this point with one equation and for the final points we replaced it here, it will give us the incorrect answer. What we need to do is find the time for the first part of the motion that goes up, then find the time for the second part when it goes all the way down. And at this point, we're going to start filling the table, the knowns and unknowns.
So I have a quick question. So we're saying that the acceleration is negative when it goes up, right?
Yeah.
Why is it still negative when it goes down?
Okay.
Shouldn't it be positive because it follows the direction?
Well, the acceleration is especially the acceleration of gravity is irrelevant to the motion that we have. The Earth doesn't change its direction of acceleration based on how the objects are moving. Acceleration of gravity always points downwards to Earth. So if ground right here, acceleration will always point downwards. The only thing that we need to worry about is giving the sign for the acceleration based on the coordinates. So down is negative, so our acceleration will have a negative value, but it will not change sign if the motion changed direction. Acceleration is always down, it will always be down, and it's based on our coordinates. We will define its direction and it will not change. All right, so we'll start defining knowns and unknowns in here. So I will, since we went through a similar process in the first problem, I will go over it a little bit quicker than usual. So t, the initial time, it will be 0. And the time where the ball reaches to the top, we don't know that yet. So I'm going to call it t top. And that's something we need to calculate. And the time it takes from the ball that when it gets to the top all the way down, we don't know that too. So that will be t ground. Then the position, the ball started at position 60, which is the position from on top of the roof. Then it got to the top point. We don't know that position yet, so I'm going to call it x top. then it fell all the way to the ground. And we defined ground to be 0. So the position on X ground will be 0 meters. And now we can talk about velocity. The initial velocity was going upwards. We defined upward to be positive, and we can notice that from here, it's going upwards. It's the same direction as positive, so initial speed is positive. And we will write down in the knowns, so that would be 71.6 meters per second. The velocity at the top, as we learned, it will be 0 meters per second. And the velocity all the way when the ball hits the ground, it will be a number that we don't know. And there's always this problem that we think that, oh, it hits the ground, it should be 0. But when it comes to when it comes to calculating velocities, we know it's going to be 0 when it hits the ground. But what we care about is the speed of that ball right before it hits the ground. And that's a number that we don't know and we could calculate. And we're going to call that V ground. All right, it looks like we are a little bit short on the time. So what I will be doing is I will put an outline to how this problem will be solved. And this outline should get you to the solution. So the idea of this solution is I want time for the first part of the motion plus time of the second part of the motion. Now, to get the time for the first part of the motion, we can look at our knowns and unknowns. We will focus on only these information because we only care about the initial to top. And what we care about is the time. So this variable right here. So what would be the kinematic equation that we can use with our knowns and unknowns to calculate this time? So we know the distance, the initial distance, we know the initial velocity, and we know the initial time. So let's look at the equations that we have. For the first one, we don't know this variable. We don't know the point at which the ball hits a velocity of 0 at the top. So we don't know this one. We don't know the difference of time. Actually, no, this is the initial time right here. And this one is difference. Okay, both of these are delta t, and we don't know that yet. So we can do this one. We can go to the second equation. We know that the velocity at the top is 0. We know the initial velocity. We know the acceleration, and we don't know the distance. So this equation will get us the x top. And that could be useful to us, but that means we still need another step to calculate the time. So let's explore the other equations. We know v final, we know v initial, we know acceleration. Oh, and this is the time that we don't know. So it looks like this is an equation with 3 knowns right here, and the only unknown is the time. So it looks like that's the best equation to use. So it will be used to calculate the time for the first part. So we will use v final equals v initial. It's v final equals v initial plus acceleration times time. So from this equation, we can find the time for the first part. I can do the substitution for it quickly. We know the v final is 0. We know that the v initial is 71.6. And we know that the acceleration is negative 9.8. And this t is the delta t. So it's the t initial or t final, which will be in our case the t on the top, t top, minus t initial. And I will go a step further, and we will get the following equation. We don't know t top, and t initial is 0. We solve this, we get the time for the first part. In the second part of the motion, we'll do a similar analysis where we can analyze the knowns that we have for this part of the problem. Keep in mind that when we do that, we will we'll have the time right here. So that's a piece of information that is useful. So let's look at the equations, or let's look at the knowns first. We know acceleration. We don't know v ground. We don't know t ground. X at the top, we don't know it. And we know that the initial velocity will be 0 because it will be coming from the top. So let's look at the equations that we have and see if there is anything useful that we can do. All right, so we'll look at the first one. This is the final x, and this will be the ground in this case. So we know that to be 0. This is the initial x, and this is in our specific situation for part 2. It will be x top, and we don't know that yet. We didn't calculate it. We have v naught. We know it. We know it. The delta time for part 2, we don't know that. Acceleration is known, and this delta time, again, it's unknown. So it looks like we have 3 unknowns, or 2 unknowns, and we will not be able to use this equation. So we'll go to the second one. We don't know the final velocity. This is the velocity at the ground. We know the initial to be 0. We know acceleration, and we don't know the distance from all the way to the top all the way to the ground. So this is unknown too. So we can't use this equation at all. We'll come to this one. We don't know the final velocity when it hits the ground. We know the initial to be 0. We know acceleration, and we don't know the difference in time. So we can use this one too. And it's the same case for the last one. So it looks like we're in a situation where we don't know what to do. So the solution to this is to go back and find x top right here, and that will make one of the unknowns in this equation known. Which one it is? This one. So we will know this number right here. We can use it. Oh no, not this one. We will know this number right here in this equation. We can use it to calculate the final velocity, which is unknown. And from that, we can calculate the time. So let me outline that real quick, and we'll wrap up this session. So we need, for this part, find x top using information from the first part, and that will be the equation we will be using. This equation right here will be x initial plus v naught t plus at squared. And keep in mind that this initial velocity is the initial velocity from initial point, and the time here, the difference in time, is the time for the first part that we found in this section right here. So this is the t top. So we'll find x from that. We'll take x and we will replace it in this equation. It will be the x at the top, and we can replace it inside the delta x, which is x final minus x initial, and that will get us the final speed. We'll take the final speed, and we can replace it in the final equation. It could be this one, or this one again. We need to get the time at this point, so we'll replace it with the last one. It will be this equation, the last one. So we will have delta x equals v initial from plus v final over 2. This v final will come from here, and we'll multiply it by the time. The only unknown is time, and that will be time ground. And the time for the time that we're looking for will be the addition of time total, which is what we're looking for, will be the difference, the time for the first part, which is t top, minus t initial, plus the difference for the second part, which is t ground, which is the final time, minus t top, and that will give us the time for the entire motion. This is a more complicated problem. It has a lot of steps, but as long as you follow this outline, it will be okay. So this is the t that we're looking for. After we calculate it, it could be substituted here. So for anybody in the chat, if you guys want to complete the problem on your own, you can take a little bit of time, take a picture of this outline, and to solve this problem. This is an interesting and important problem to go, just because it has a couple parts. Isaiah, I think this will wrap up our session for today.
Yeah. So again, we will have this YouTube link up in a couple days, so you can go back and rewind if you missed anything. And to note, our next normal SI session for me would be Monday from 11 to 12 p.m. at SSC 601, and Hassib will be Monday as well from 1:30 to 2:30 at SSC 602. And then our next virtual SI session won't be until 2 weeks from now, and that is October 14th at the same time. So thank you again for coming to our virtual SI session.
All right. Thank you, everyone.
All right. And
thank you, Isaiah.
Yeah.